Hey, so now let's have a look on to the discussion for the next question. So here we have this question number 19, which stands for 3 marks, and in this question also we were given the choice. So this is the first choice of question number 19. This says define the term wavefront using Hydrogen wave theory, verify the law of reflection. So here we need to prove the law of reflection using the wave theory. Okay, so first of all we will define the term wavefront for this question. So what is wavefront? The region where the wave is propagating, geometrical structure formed by joining all the points which are vibrating in the same phase are said to be wavefront. So wavefront are the geometrical structure which are obtained when you join all the points which are vibrating in the same phase. Okay, moving further, in this question we were also asked to prove the law of reflection using the wave theory. So for that you can consider here a plane wave ABC that is incident at an angle I on a reflecting surface AD. So this is my reflecting surface AD. ABC is the wave that incident on this reflecting surface at angle I, that is the angle of incidence. Further, if I say that V is representing the speed of the wave and delta t is the time taken by the wave to move from ABC to B1C1 and also from B1C1 to point D. So the wave ABC is moving from ABC to B1C1 and from B1C1 to point D. So delta t is the time taken by the wave in moving from this to this and from this to this. Now, when the disturbance reaches from point C to point D at the same time or in the same time, what is going to happen? There is going to be the formation of the hemispheres at point A and at point B1. At point A, in that particular time, what is that time? Which is 2 delta t. Okay. So here in that particular time, which is 2 delta t, the wave has formed a hemisphere of radius 2v delta t, and the same hemisphere will be formed at point B1 having the radius v delta t. Okay. So this is what I have already mentioned here. So at the time when the disturbance of point C reaches point D, disturbance of point A must have formed a hemispherical shape of radius 2v delta t, because the time that the disturbance has taken from point C to D is 2 delta t, and at point B1 it must have formed a hemispherical shape of radius v delta t. Okay. Now if we draw a common tangent from point D to both the above mentioned spherical envelope, we shall have DEF as the reflective wavefront. So now further what we need to do is we need to draw the tangents, that is a common tangent cutting both the hemispheres. So we will be getting DEF as the reflected wavefront. Okay. Now here is the formation of these two triangles that you can see. So if we have a look on to the triangle ACD and DFA, where is the triangle ACD? ACD and DFA. What we are going to get? See here, I have drawn the triangle separately. So these two angles are 90 degree. Now here in these two triangles you can see, I can just mark. So angle ACD is equal to angle DFA, both are 90, and also here you can see AD is equal to AD, which is common to both the triangles, and CD is equal to AF, that is 2V delta T. Okay. So by RHS rule both the triangles are congruent, and as the triangles are congruent we can say that angle I is equal to angle R, and hence the each corresponding parameter must be the same. Okay. So it means both the angles, that is I is equal to R, and this is how we have proved this reflection law by using the wave theory. I hope this discussion is quite clear to you. Now let me just explain you the marking scheme for this choice of this question. So here in this question we were first asked to define the term wavefront. So when you will define it correctly, you are going to get 1 mark for this. Okay. Further, for the remaining explanation you are going to get 2 marks, and how the marks will be divided, let me just explain you that. So you will be getting half mark for drawing this diagram showing all the wavefronts and the waves. Then you will be getting half mark for this explanation. Then you will be getting half mark for proving the congruency of these two triangles, and then you will be getting the remaining half mark for writing this result, that how this angle of incidence is equal to angle of reflection. So I hope this is clear to you that how in this particular question you are going to get 3 out of 3 marks. Now let's have a look on to the next choice of the same question. So here we have it. This says define the term refractive index of a medium, verify Snell's law of reflection when a plane wavefront propagating from a denser to the rarer medium. So basically this question demands you to prove the law of refraction using the wave theory. So let's have a look on to the solution for this question. So first of all we will be defining the term refractive index, which is the factor by which the speed of light gets reduced with respect to the speed of light in vacuum is said to be the refractive index for the medium. Or you can also define it as the ratio of the speed of light in vacuum to the speed of light in the medium. And you also need to mention there that this V stands for the speed of light in medium, C is the speed of light in vacuum, and mu is the refractive index for the medium. And if you have written this all, you have successfully answered the first part of the question, which wants you to define the refractive index. Now the next part of the question wants you to prove Snell's law using the wave theory. So here for that you can have a look onto this diagram where I have taken up these two mediums, medium 1 and medium 2. So here B1, B2 is the incident wavefront with V1 as the wave speed, and A1, A2 is the refracted wavefront in the other medium, as you can see, with V2 as the wave speed. Now when point B1 traverse a distance B1 A1, so you can see here when this point B1 travels this distance B1 A1 in time capital T, you can clearly see that this will be equal to V1T, because V1 is the wave speed in medium 1. Okay, the wave front originated from point B2. See here, this wave front that is originated from this point B2 must have travelled the distance V2t in medium 2 in the same time t. Now here if we consider the incident wavefront B1 B2 and the refracted wavefront A1 A2, I can write here that sin I is equal to B1 A1 divided by A1 B2. You can see here from this triangle, this is angle I and this is 90 degree. So in this right angle triangle you can see what is going to be sin I, that will be perpendicular upon hypotenuse. So this will be A1 B1 divided by A1 B2, that I have already written here. Okay. Similarly I can write sin R. See here, this is R. So here I can write sin R as B2 A2 divided by A1 B2. Okay. So this will be A2 B2 divided by A1 B2. So if I just consider this to be as equation 1 and this to be as equation 2, on dividing these two, this is what you are going to get, the sin I by sin R is V1 by V2. Now what will be V1? You can simply write V1 by V2 as mu2 by mu1 from the definition of refractive index. So this is how we have proved this Snell's law by using the wave theory. Now let me just explain you the marking scheme for this question. For successfully answering the definition or the term refractive index, you are gonna score 1 mark. Further, for the next part of the question, you are going to get 2 marks, out of which you will get half mark for drawing this diagram. You will get half mark for explaining that how the wavefront is traveling from medium 1 to medium 2. You will get further half mark for explaining this relation of sin I and sin R, and you will get the remaining half mark for finding this final expression. So this is how you are going to get complete 3 out of 3 marks for this choice of question number 19. I hope this question is also very clear to you. Now let's move on to our discussion for the next question.